Hi there. Can I just? Actually, no. I was gonna ask how many people here are involved in any sort of offence-related stuff, or is it? Okay, cool. Yeah. So I'm going to apologise. Sorry, I'm going to introduce myself first. I'm a pen tester with NCC. I've been with them for 2.5 years. I mostly do stuff relating to AppSec. I do some hardware and embedded stuff, do a little bit of automotive. This is probably going to have some bearing on the rest of the talk. I'm not actually a formally trained engineer, but I'm striving that way because I think it's quite important, and I think there's a degree of there's a need in pen testing, and particularly offensive security, to increase the quality of engineering perspectives in the way that we approach offensive work. And I hope it's also going to feed back into better defensive mitigations and responses in general. So I'm going to start off with a short and fairly unfair caricature of pen testing based on some standards that we have for what a pen test looks like. And I'm going to make a case for my adverse engineering sort of perspective on things. I'm going to walk through some work that's sort of kicked me off down this track. Has been really inspiring me. I'm going to do a walkthrough of how I've applied it. I've got a disclaimer here. First of all, this is very subjective. This is very much my own opinions and not any sort of official position statement from my employer. And the perspective that I've got is from day to day, just doing pretty much completely offense. So I'm very aware that anyone working from a defense point of view probably has a very different perspective on things, and that there's a lot of things that I don't necessarily have as much consciousness of when I'm sort of developing my ideas in this respect. I kind of don't want to tread on people's toes in that respect, and I'm just very aware that I've got blind spots because I just break things, and other people have different priorities. So in terms of what a pen test is, we've got this classic pen testing methodology model, and it's a standard that's sort of incorporated into CREST, into OSCP standards, into CEH, and all the rest of the various different accreditation bodies and standards. None of them in particular, I'm not calling them out particularly, it just is a part of all of them. And there's this idea that we've got these stages that are scoping, intelligence gathering, potentially, threat modeling, enumeration, exploitation, post-exploitation, and then reporting. And there's a sort of life cycle that has certain flaws. So the scoping stage is typically, there's a degree of wishful thinking involved. The client doesn't necessarily, as was mentioned by in a previous talk I attended today, the client doesn't necessarily always know what's involved in their system, so the scoping procedure is often theoretical because it's in the absence of the system itself, usually. Then we've got intelligence gathering, which is often using search engines and aggregators and various other things related to social media. We've got theorizing about the potential security environment, which we haven't looked at yet, typically. We've got scanning things. We've got rummaging through not just exploit libraries, as in things that you can download, but rummaging through the sort of things that we've exploited in the past and that we know are potential issues, and trying to apply all of that information that and experience and expertise that we've got to the target. And then once we've breached it, doing build reviews and then telling the client bad news. So I'm claiming here, possibly being slightly flippant about it, but I'm claiming that this is essentially, from the technical security point of view, this is goofy cyber warrior stuff, and we're focusing more on the idea that we're attackers and less on how do we solve the problems that we need to solve to get from outside of a system to inside of a system to the resources and assets that we want. And that we're focusing more on the sort of life cycle of an attack and a threat and a kill chain. And this comes back from the Lockheed Martin cyber kill chain concept, which is is absolutely critical if you're threat hunting and trying to understand how people persist within neural networks and all of that stuff. And it turns pen testing into a sort of cyber warfare exercise, but it doesn't really inspire us. It doesn't create guides to how we don't have, this is focusing on the game and not the technical challenges that we're actually facing. Although it is nevertheless a really good way to bound scope for testing into sort of commodity units that can be sold, it's not necessarily useful as testers. So security, particularly from an offensive point of view, is decided by your capability over the target system. It's not decided by the lifecycle processes in particular. And this idea of the pen test lifecycle is descriptive of what happens in general, but it doesn't prescribe how we should go about doing it. And it leads us to not necessarily have a great bigger picture about the connections between the different silos that we have. So we have, in pen testing, there's typically people who are inf people, or people who are web people, or people who are involved in IoT and embedded stuff and hardware, and we have these different silos, but we don't have an idea of what it is. We don't have good common ideas that we share with each other very effectively about what it is that's common in the ways that we've developed the information that we've developed through hacking into things. And getting some sort of bigger picture of that is kind of critical because there's new technology coming out all the time, and we need to continually be innovating, finding ways to get through things. We need a bigger theory for dealing with all of the hows, how am I going to do this that we need to get through. So how do we create new tools? How do we investigate new protocols? How do we review build security in places where there is absolutely no best practice? And we're seeing new frameworks coming out all the time. And understanding how we go from this is something that, you end up with requirements saying we need someone with 5 years expertise in this 2-year-old framework, that you need to be able to bootstrap from the information, from the framework not even having existed very long, to having an ability to act on and hijack that system, or understand the ways that it could be hijacked in order to protect it. And I think there's a parity here between offense and defense that I'm hoping is kind of clear. And also we need to also get to the root causes of vulnerabilities. So a typical example that comes up a lot is XSS or SQL injection, and the idea that what we need to be doing is correctly filtering all of the bad stuff that is potentially going to result in a thing being rooted or not.
Sorry, can I just interrupt for 1 second? Is there a Nathan Hendry in here? No, Nathan Hendry? No, sorry, apologies. Sorry.
And if we actually step back from that sort of thing and we understand it on an engineering level, it's not, and this has become clear in the years since SQL injection first started being found, the issue isn't that we need better, bad, evil filters. We don't need to find malicious inputs. What we need to do is create systems that we can trust to handle any input, regardless, in a valid and safe way, which I'm going to develop on a bit later. So a couple of sorts of scenarios. The perspective that I'm putting forth here of like all of this high-minded philosophical stuff about pen testing is quite resource intensive. Frequently, there isn't time for it on any given pen test. Occasionally, you have a few spare moments to work through some of this stuff. But there are cases where specifically pen testing type assessments do lead to this sort of thing specifically. And there's cases where we find oddball projects, new technologies, where we have to validate a third-party vendor assurance claim in some way by trying to scrutinize and look for gaps in things that they might have missed. Trying to go beyond compliance in cases where there's like an ongoing long-term business risk, and you're not just getting clients who want a tick on the box kind of test where they're willing to invest and have a much deeper look in things. For instance, like in M&A is a really big example of that. And also generally typically in research scenarios where you're just trying to look for new things that look at things in a way that people haven't looked at before and trying to develop new ideas about how things might be able to fail. So from an engineering perspective, I've completely cribbed this definition from the American Engineers Council for Professional Development because it was the shortest and clearest example that matched what I'm trying to argue here. Engineering is the creative application of scientific principles to design and develop structures or to construct or operate the same with the full cognizance of their design or to forecast their behavior under specific operating conditions. So, and that's what pen testers, before we get to the reporting stage, that's essentially what we're trying to do. We're trying to understand the nature of how the system works. We're trying to build things in it. It's essentially a hostile environment, and we're essentially developers up until that stage where we need to report what our capabilities are and how those could have been mitigated. So my argument here is that we can try and deal with the challenges that we come up with by applying scientific principles, by making experiments and constructing tools in order to build on the clients or the targets or whatever environment. And for me, this is more like stepping back from the whole think like an attacker thing, which is such a big cliche around how do you hack things? You think like an attack, like what does an attacker think like? And why does it matter what they think like? What attackers were unsuccessful and how can we do better than them? I'm putting here that thinking like an attacker is probably not as helpful as just getting on with being engineers and developing capabilities. And we've got this, because essentially we're in this was pointed out by Sergei Bratis a couple of years ago. We're scientists. We develop proofs about unexpected behaviors of systems that are different from the shape of the thing that the developer thought that they built. We come up with hypotheses, we make experiments, and we prove true or false whether a system is exploitable in a particular way. Well, this is something that's a standard part of what we do. It's not a wild departure, it's just something that we don't really have a formalization of, and we don't necessarily formally think about it that way. So one of the things that really kicked me off in this direction, thinking about things in this way, was seeing this talk from Trey Forgetti in DEF CON a couple of years ago, where it turned out that there was a major incident. Several regional 911 networks got taken down by a trivial cross-site scripting attack in an iPhone, which was put on a prank website and then shared over social media. And the interesting, the really boring thing is how the actual exploit worked. It was just a URL for dial this phone number and click the link that was embedded in the page. The really interesting bit was that actually the reason that the phone networks came down, at least according to Trey, was that there was a lack of ongoing provision. As the number of users on the phone networks had increased, they hadn't actually brought up the level of the number of nodes in the system. They hadn't brought up the ability to sustain the amount of traffic that could potentially be driven by a bunch of users. And what we've got up in the top right-hand corner is this Erlang's B formula, which says this is the probability of network blocking with a certain number of nodes in the system, and you can actually calculate, this is how we predict what we need in order to, you can invert the formula and you get how we predict what we need in order to resist a certain scale of attack. And that's sort of wider scale thinking, trying to think in an engineering sort of perspective, rather than just going, oh, well, it's an XSS, we can fix that XSS, we'll just cross off that URL handler or make sure that it can't be clicked from JavaScript. Rather than doing that, we need to be trying to elevate and think, what is the bigger picture going on here from an engineering point of view? Why are these systems failing? At what scale of protection and mitigation can we win the game? Another area that's been a massive inspiration for me has been cryptography. Cryptanalysts and cryptography engineers. Cryptanalysts are people who break codes, for anyone who doesn't know. Cryptography engineers build crypto systems, and there's been a mutual language over the years built up out of these fundamental attack models, such as this is in CPA, which is indistinguishability under chosen plaintext attack. You've got in CCA 1 and 2, which are indistinguishability under chosen ciphertext attacks. They're two different types, hence the numbers. We've got models of data integrity and non-repudiation, but the really important thing that having that formal language gives is that you've got a formal understanding of what sort of protections are appropriate to which sort of context and what you actually gain or what you can trust, which is really important because, as is pretty notorious, trying to develop any sort of crypto is a complete minefield. It was absolutely necessary for them to develop this language of attack models and defense models in order to be able to actually reason about the systems properly. Another big inspiration for me in the last few years has been LangSec, which is essentially taking fairly basic computer linguistics and programming language theory and taking insights from that to start saying, how do we deal with bad data? How do we deal with bad input? And when can we know that we're going to win? When can we know that we have a chance at winning against dealing with an arbitrary input? So, and the outcomes of this are things like no shotgun passes, which is to say, you validate everything and then you do all of the processing that you might be doing. You do not do those together as a mixed process. Throw out Pastel's law, which is the older computer development, software development principle that you accept input liberally and you send out output more conservatively. What's been shown is that if you accept input liberally, if you accept slightly invalid data, that you're actually just shooting yourself in the foot and giving your attackers much, much more options for bypassing any of your filtering, any of your attempts to sanitize or protect yourselves from malicious inputs. It also, there are like basic things from Turing era that if you have an input language that's Turing complete, you cannot do enough computing on that. If you have an input that's even deterministic context free, which is slightly less complex linguistically in the Chomsky hierarchy, which is it's a set of computer linguistics concepts, but if you have a certain degree of programmability in the input data that you're trying to pass, at some point you cannot ever guarantee that you will not be that you will know how that ends up in your system, and that's a really, really important thing to recognize if we're trying to make systems that we can trust, essentially. And it also develops this idea, and kind of off to one side because it's fairly vague and informal for a lot of the earlier LangSec stuff, but it develops the idea of a weird machine. And a weird machine is the machine that happens to be all of the unspecified behavior that is latently living in your system that you didn't necessarily deliberately put there, but you did kind of put there by accident. And then hackers go and program that weird machine rather than the machine you intended to invent. So the final example I'm going to give before I move on to how I applied this whilst hacking things is this paper by Halvar Flake, Thomas Dullian, which is called Weird Machines, Exploitability, Improvable Unexploitability. He takes all of the finite state machine theory from like typical computer science education and starts formalizing the idea of an exploit and formalizing the idea of the intended machine and the actually implemented machine in the concrete implementation. and starts formalizing our understanding of, which is an understanding that exploit developers have had for decades. It's not like all of this stuff, from the philosophical point of view, all of this stuff isn't new ideas. And he says that in his paper as well, all of this stuff isn't new ideas. It's more that we don't really talk about each other, about what we're doing at this sort of scale typically. We talk about, well, I've bypassed ASLR by leaking a pointer from some place and then doing this and that, and it's very, very low. We're very close to the bone where we're dealing with that stuff, and we're not really communicating in what's happening at higher scale so that we can make more fundamental changes, and understanding how we find those sorts of issues on a more fundamental level. So, key ideas that I'm putting across. I'm hammering these, sorry. Maintain an interest in the theoretical fundamentals of your domain. So one of the things that I've heard a lot of people working in security say, specifically people who went into computer science formally, is, I've never used any of this, why do I need to know about finite state automata or, all of these other things, these abstract theory things that are just not relevant to breaking into a system or securing a system or reviewing firewall rules, and it isn't directly relatable to that stuff. We have to make those connections, and we have to make those connections at a big enough scale that we can make better judgments about how to fix them rather than fixing one firewall rule. If you have the resources to do so, if you have the time available, which admittedly it's pretty rare, but it happens, try and go beyond looking for the existing solutions for unsolved problems. Try and find potentially new ones. Try and develop your ability to understand the problem a bit better. Start making experiments for it. And keep yourself a healthy skepticism about, we all have these received understandings of how things work, right? And those need questioning on a regular basis, because it's a big place where all of us are prone to fall down on from time to time, because there are plenty of things that just shouldn't work. And we're in the business of finding out what shouldn't work but happens to really actually work, and then fixing it, making sure the machines are more trustworthy. Okay. So what I'm arguing for is stepping back from the vulnerability first point of view here, because vulnerabilities are sort of a long way down this chain. They're not what we're starting with. And if we start with looking for vulnerabilities, then we're kind of closing our minds off to all of the other ways that vulnerabilities people hadn't really thought of yet end up. We need to be a bit more creative. We need to test them. If we're thinking like engineers, we're looking for ways to build bridges across gaps. We're looking for ways to build bigger levers. We're looking for ways to, often simply the difficulty of operating within a system that you've got a limited understanding of is difficult itself, and being able to build that ability on a short time scale is really, really useful. So I was quite irreverent to start off with about the core model for pen testing. There's most of the cases where it's not really possible or relevant to go into deeper computer science type theory stuff. I'm not trying to slam anything really, but I'm trying to argue that there's a real motivation and there's a real need for us to be taking a bigger picture look and looking across, bridging gaps between different information security silos and trying to understand the sort of things that join different fields together at a higher level. So my example from my own experience, once upon a time I was investigating an IoT gateway device. It was based on a Java firmware system with some proprietary JVM. There was the device itself bridged to some back-end network over GSM, and the back-end network was on a private APN, which is private access network. So from a capability of point of view, owning that device was interesting. But bearing in mind it's a gateway to another realm, what I really want to do is be a bit more grandiose about things and see if I can take it a bit further. So, being a GSM device, it has an eSIM for connecting to a private network. I don't know what's on there. Are there routes to own all of the other devices that are also connected to this network? Is the backend interesting in some way? I've got questions, and I need to find out how do I get answers. So I've got a device. The device is somewhat restricted. Can I build a device that will do the things I want to do? And yeah, pretty much. There aren't any freely available ways to plug an eSIM into a mobile dongle. However, you can just solder wires between them. It's just a hot iron and a bit of time fiddling with some tweezers. However, in order to get through to the APN, you need creds. And this is all kind of typical pen testing stuff. You look through the Java environment for something you can exploit to find the creds. You look through data on the eSIM for creds. You sniff data on the buses for creds. And then eventually, in this case, I found that I found file chunks, zip file fragments, which, if you're familiar with Java, then obviously Java jar files are in pkzip format, and I've found my J2 embedded data. So at this point is where I hit my brick wall in the usual methodology, which is where the rest of the talk becomes relevant. Binwalk yields corrupt garbage or incoherent decompression, which is to say Binwalk immediately fills, when I unzip things using Binwalk, when I try and unzip the fragments of compressed file, my hard disk immediately fills up because the corruptions in the deflate stream completely hose my hard drive and don't actually turn up any useful data. We can see that the data is fragmented, shuffled out of order into regular size pages, but there's no common file system indicators. That being an embedded system, there's a custom operating system, there's a custom file system. It's writing the files in pages, but we don't really know much more than that, and there's a hell of a lot of reverse engineering to try and figure out how the file system works. I can't even find any page tables. It's starting to look a little bit sad from a pen testing point of view. So I've got a demo here. Excuse me. This is me running Binwalk on the dump, on the memory dump. And you can see all of this zip archive data, which is lovely. It looks really promising. You try and decompile one of the class files. Oh, nothing. Really, really sad. So Binwalking it didn't really work out. So at that point I go, well, I'm really, really keen to try and sort this out. So data storage theory, zip files, whether you're, I don't know if anyone's into like file forensics and file format type stuff, but zip files are really unusual compared with a lot of other compression formats in that there's lots of redundant data internally, there's lots of internal metadata, they self-reference, they tell you things about what sort of operating system it was zipped on. Different parts of the zip file point to each other, and this structure forms a sort of a tree, which is going to be useful later. I've completely, at this point, given up on reverse engineering the file system from some kernel drivers in the memory dump somewhere. There was a lot of obvious code there, but it was going to take far too long for me to do anything useful working that out. And also, at this point, I realized this is actually quite an interesting sort of puzzle-solving problem. I've got data that tells me at least pieces of information about how the file ought to be structured. I have the fragments of file that have been shuffled out of order, and if I assume, for argument's sake, that I've completely lost the file system information, can I use that information from within the file to start piecing the file back together into the correct order and decompress it? So here's a picture from Angel Bettini's Kokami project. It's like really, if you want to look at any file format, there's these amazing diagrams in Angel's GitHub, which will walk you through all sorts of different file formats, but in particular, this one's a zip file, and you can see it starts with a series of local file headers and file data, and then you have a directory, which is convenient, and then at the end of the file, you have the end of central directory record, which is a pointer back to where the directory starts. So you have a sort of listing for where different parts of the zip file are supposed to be, which is pretty useful. Looking at the dump itself, you have these different pages, and I say pages, I'll just skip ahead a bit here. You can see this is sort of an example of what a page looks like. So a page has been written at 80400, and that page ends at 80800. This is a 1 kilobyte page. And you can see here that it's really obvious that the entire data type, like these are three different fragments. One of them's ending, one of them's fully visible here, and one of them's just starting. And those have been shuffled out of order in that way. And we can see that, like, the page size that this system has been written in is a 1 kilobyte page size. So, if we start looking at these pages that are in the file system, we see things like this. We've got like pages that are just central directory blocks. We've got pages that are bits of compressed data stream with local file headers spread through them. We've got a couple of end of central directory records in there, and so on. So we can see, for instance, the second one from the bottom is where the central directory starts. We can recognize that because it's where the data ends. And these things happen up one after another, and that's where it happens. So we start building a model of the file in little pieces. We're going to start with the end, because the end of central directory happens only once in a file, and that at least tells us, at the very least, how many files are we looking at in this dump. It's also got a very easily searchable magic value, pk 5 bytes, 6 byte. So we search for those. It also tells us the size of the central, as well as telling us where the central directory record starts, it tells us the size of the central directory. So we have like a bird's eye view of what the file's going to look like. And we search through the system, and we search through the dump, and we find 2 of these, which means we're looking at 2 fragments. It's a little bit problematic because the internal pointers within the zip file in the central directory, which is like the library of files, the internal pointers are only relative to the start of a zip file. So if you have 2 zip files, you have 2 starts of zip files, you need to disambiguate between those 2 different groups of file fragments so that you can reorder them correctly, separately from each other. So how do we classify them? That's the classification problem. It's I hesitate to say machine learning. Someone said machine learning to me when I explained this to them at a previous event. But we have classification vectors that we can take and turn this into a classification problem and use the k-means clustering algorithm, which will take a bunch of data, it will take the classifiers, and it will separate those into a pretty reasonable estimate. And you can see here, what it does is it puts values randomly within the data set and then moves them so that you maximize the separation, the classification. Those lines are splitting the data in this example that I've cribbed from Wikipedia. And those lines move until it more accurately represents the data set as a whole. You don't really need to know this because you can just figure out what the classifiers are and plug them into k-means anyway. It's just one in the SciPy library. You can just import module and crack on with it. But it does help to understand how these clustering algorithms work to the extent that you understand why they're going wrong when they do go wrong. So we've got lists of the separate central directory headers. We've got lists of separate headers in general, but in particular we've got lists of the two separate lists of central directory headers that we've clustered based on the things like the compression flags or the timestamp or things like that are going to be distinct between two different builds. So in order to reorder them, we also, in those headers, I don't know if the text is too small, but we've got the relative offset of local header, and this isn't a part of the pkzip specification, but a pretty much necessary part of writing a zip file if you're compressing a bunch of data into a zip file format, is that you're writing it from the start of the file to the end of the file. You can, but you don't typically, and a lot of file format stunting involves not doing this, but typically you're going to be starting with the start offsets and working your way through, adding more data on as you go. So we can use those local file offsets as a correct ordering for the central directory headers. There's like free information there. And by taking the pages that we found those CD headers and then reordering those pages, we get something like this. We get a fully formed central directory back. We get the end of central directory at the end of it, because all of those pages that those were on are correctly resequenced for their relative file. We don't know what's going on in the rest of them. There's a lot of gaps for the rest of the sort of skeleton model of a file we're building up, but we're getting there. So the local file offsets point to corresponding portions of the file that we haven't filled in yet. And we can find the local file headers for those central directory headers because they pretty much have all of the same data. This is the redundancy feature I was talking about with respect to zip files. All of this stuff we can just make what we expect to see in this local file header and then do a binary search through the memory dump for that, and then put it where the central directory header says that local file header is expected to be. We don't just put the header in there, we put the whole fragment that we found the header in, and we end up with a picture more like this. We still have gaps, but we have the benefit now of any of that data that was broken or corrupted by being on a page boundary is now lined up nicely. So we've recovered the stream in between there. We've recovered quite a lot of the data because we've got the run-on effect between different fragments that we've been able to put together. We're left with only a few holes in the overall dump. So I'm going to just... Okay, so here's the script that I wrote that automates all of this stuff. It's searching for the different headers. You can see it's found 924. It found roughly 1126 there in the other one. We've got a percentage recovered of about 78%, and or 70% in the other case. So I'm going to start unzipping those and start looking inside of them. And here we go. So, sorry, that's kind of skipped some of the stuff there, but inside there's a configuration file, and in the configuration file there's some general purpose creds for, and that was essentially what I was looking for. There's also a lot of other data that had been reconstructed usefully, and that's something that just wasn't there when I was trying to just bin walk the file and unzip the fragments as they were. So, and that's like start to finish, that's my goal one with some clustering algorithms and that's job done with some clustering algorithms and understanding how a file system is put together and how it works. There's some limitations to the solution, which is on GitHub. I can't recover any data segment that's bigger, where there's a gap bigger than a 2-page size. Worst case is pretty bad, but it does recover a lot of the data in the cases that I've been looking at. I haven't made use of the fact that there's also CRC data, so I could hypothetically be brute force searching for CRC for chunks which could be fitted into holes and then make the CRC values validate. There is a problem with that potentially in the long run for bigger chunks, because you end up brute forcing a series of chunks that might turn out to match the CRC value, but not actually be the correct ordering of chunks in order to decompress to anything useful. So there's like benefits and downsides to taking that approach, and I didn't really go there because it wasn't that helpful. So anyway, that's pretty much everything from me. Does anyone have any questions or?
You're not allowed to ask questions.
Oh, okay.
So you're talking about doing a better pen test. Is calling it a pen test part of the problem that the client has an expectation of what a pen test is? Should you consider the word hacking loss, the word pen testing loss, and come up with a new term for the kind of testing that you do? Because it's easier to define a use case than try and change the customer's expectation.
That's a marketing issue, I think. So I've kind of taken for granted that the issue I'm really looking at solving here is the technical issue of how to deal with unforeseen issues, unforeseen situations and environments, and building good solutions in them, building quality solutions and quality advice and guidance. I think, strictly speaking, this sort of methodology that I'm proposing is much, much better suited to more in-depth reviews, and whether it's called a pen test or not, it's more suited to time when you've got more time available and investment from the customer. So, like I said before, M&A type situations where they want to know that, like, not just is this safe from all commonly known vulnerabilities right now, but how much risk are we at 5 years from now because of the general quality of what's going on, and what sort of things might we be nipped by, for instance. That sort of thing where there's a big motivation to do a much deeper level of assessment going on. But again, I think I don't think what it's called really matters. I think I'm mostly just making the case that actually computer science is really, really much more useful than people give it credit for, and that a lot of people in InfoSec have got some sort of computer science background and possibly are kind of doing themselves out of the benefits they could be getting from applying it.
Anyone else? All good? No? Thank you, Phoebe.
Thank you.